realize that. And then that was bad, very bad. So as of this month, the California in a long time is 100% within drought, extensive drought. Okay? And then with just some pictures here showing you the before and after pictures, reservoir with water, reservoir without water. And the impact of that has affected a broad range of life and economy as well. Here, these are just some of the snapshot of news piece. So, as meteorologists, as climatologists, we try to understand what is the mechanism, physical mechanism, in terms of dynamics, physical process, causing this standing ridge pattern that was really the meteorological cause of this drought, as well as the cold in the east. Okay? The very important missing piece is the climate driver, because if you look back, this past winter was neither El Nino nor La Nina. That was still the largest climate forcing that climatologists are going after. So now what? It was actual neutral. What is the forcing? Okay. So the first step we did is always to look into the circulation features. I realize not many climatologists are here today, but imagine this is just like a weather map, and you have this normal, which is in blue, and then this winter was like this. So we know that there's an immediate ridge, a very strong ridge here. It's blocking for 3 to 4 months. Okay. So if you subtract the two, then this tells you it shows the same feature, but with a very different look, which is these contour centers. So this is low pressure, this is high pressure. Okay, so with these two, and we start to give you some names, we call this dipole. And if you want to know how unusual or how common this kind of circulation pattern is, the simplest way is to pick up a point, the high center, and then you correlate with anywhere else for as long as the record goes back. The data we use will be explained to you by Wesley's next talk. And then, so this is the correlation that we got. Okay, so you can see that just by eyeballing the two figures, you can see how close the patterns resemble each other. So this is the first clue that, well, this drought and the cold patterns is not random, it is systematic. It has happened before. It has happened actually quite consistently. That is why you have these two very similar patterns. Okay, and this center here, the fact that it correlates so well, so strongly with this ridge center, means that whenever you have this ridge build up, making the west coast dry, at the same time it's making the trough deepen and produce those cold weather and cold prolonged climate in the east coast. And that actually creates some energy-related crisis there as well. But having these two combined, it gives you an idea of how you can trace back. Okay? So we use this center of the dipole, construct this dipole index, and sure enough, this past event was the record breaker. Okay? And it was extremely low, just a couple of years before, that actually resulted in some very strong atmospheric river events, Pineapple Express. Moisture being diverted into California and during that winter. So you can see that the amplitude has increased. And as climate diagnosis, we also try to correlate with or find connection with all these known major oscillations, and we didn't find one. But we did find that if you don't look at the main climate drivers, but look at how the drivers develop. For example, in this case, we found that if you don't look at El Nino, but start to look at a year before after El Nino, you could really find some signals that suggest what is going on to cause this dipole pattern to develop. In this case, we call this ENSO precursor because we found that if you correlate, pressure here with the ENSO or El Nino index a year later, you actually can reconstruct this pattern, which looks very similar to what has experienced in California. Okay, so that was circulation. Now this is sea surface temperature, giving you an idea of where the tropical ocean, the temperature changes, the heat source may be, the heat sink may be. And I'm skipping the details here, but I just want you to pay attention to how similar the three panels look alike. Okay, because each one was constructed by different way, and this was the test winter situation. You can see that it is very close to the dipole correlation. It's very close to the so-called ENSO precursor patterns. There might still be a lot of dynamics between how ENSO can have a precursor here, but we can come down to that the other day. But here is just a quick example showing you how come a pattern like this can eventually then evolve to that. And you can see this is animation is evolving gradually. So what used to be high warm water here gradually is being replaced by cold water. In the meantime, El Nino started to develop. This was a past event. This was not this event, but you can see the similarity between the two. Okay? So the idea is that, well, El Nino does not develop overnight. It takes it a long time to develop for a year or two, okay? More than a year. And if El Nino has this systematic pattern, then we have found that the conditions making El Nino to develop also reveal some systematic patterns. And that potentially can induce something we call interconnection like these. And we found that it's actually very closely related to this dipole pattern here. Okay? So, well, the next important thing is how do you examine the dynamics, and the more important question would be what's the role of climate change that make these extreme events to happen. Okay? So we run this model. This is the ANCA model co-developed by DOE as well. It's called the Community Earth System Model. And this is actually the model that performed the best in terms of depicting these so-called ENSO precursor patterns. We ranked about 18 of the 20 IPCC models, and this is number 1. So we can rerun the model, play God and run it for 100-something years. With one run, injecting greenhouse gas into the atmosphere. With the second run, you only put in something like the solar cycles, those so-called natural forcings. And then we can compare the two, okay? So now, you can see, just from the SST, the sea surface temperature patterns, the models did a good job in terms of picking up these observational patterns, cold, sandwiching these warm waters there. And you can see that it's showing more strongly in the greenhouse gas run and less strongly in the natural force runs. Okay, so this is the circulation pattern responding to those ocean situations. And again, you can see that the dipole was very well simulated there. And yet, we can find that the greenhouse gas is indicating that the relationship between this dipole pattern and the precipitation and El Nino precursor pattern is the strongest within greenhouse gas. And that's the only set of simulations that correspond with the observation. Okay? In the natural runs, we don't see that. So this is one indication that maybe greenhouse gas is impacting the weather pattern, modulating it to coordinate better with this El Nino development. Without that, you don't see that. Okay? But the more important thing really is the ridge and trough amplitude. So what you're seeing here is simply just the variance. You do a variance every 20 or 30 years running through time. You can see that the variance of this dipole pattern has increased dramatically, continuously in the greenhouse gas runs. And this is observation, and this is the natural runs. So you cannot really plus that with that and divide by 2. It doesn't work that way. So the proper interpretation is that you can see that in the natural forcing, it does not go as high as this greenhouse gas forcing. Okay. And in the real world, we have some other forces. But how about future? So this is the future runs using just the middle of the road scenarios. Okay, you can see the magnitude continue to increase, and we know in RCP runs the CO2 contents probably eventually double, or a little bit more than doubles, and by the end of the century. Okay, so what does it mean? So allow me to give you a little bit explanation graphically. It's probably easier. This ridge pattern, trough ridge pattern, or the dipole is projected to amplify. Okay, and the fact that you're seeing the amplitude increase, it means two sides. So this past winter, we saw this pattern. But what it really means is, in some years later, you can see it flip around, okay, like that. So when California experiences future wet winters, it could get wetter or more pronounced in a way. So this is what the model data is really telling us. And my colleagues from the DOE lab here in the lab just sent me this last night. So he ran something like, say, hey, if we increase 1% of CO2 every year until it quadruple after 150 years, what's going on with precipitation? So this is precipitation, winter rainfall in red. So we can clearly see that interannual variability has expanded. So the extremes will happen. Okay? And it really coincides with just the climate report released by White House yesterday. But what's more, I think we, as climate scientists, we want to know what is driving this. And I believe we found some clues. So how about the prediction? Because the extreme events can only be so damaging if you don't know it's coming. Okay? So unfortunately, right now, the current performance of climate models is just not there yet. Okay? This is just some archive from this national multi-model ensemble efforts to think of it as 18 models, the better performing models put together, simulating or predicting this winter precipitation anomaly. So this is the real one. This is projection. It's actually wet. So this starts from August. Okay. So every month they upgrade that. This is September and October. So after October, when the drought has started to develop, the model start to see the signature here, predicting this west coast to be dry. Finally get the right trajectory. However, in the middle of the drought, you can see that predicting from November for January, the model reverts back to wet condition again. Okay, so there's a lot of variability there that is compromising the model performance here. Okay, but we do think that this drought or the climate forcing is traceable. Okay, and here's some examples. And if it's traceable, it means it's potentially predictable. Okay, and working on toward this direction. It's just a quick explanation of how we can trace it back. If you consider the atmospheric wave pattern like this, we can compute this wave energy flux. And then what it does is that it's not like you are throwing ropes like that. Okay? It simply amplifies after you receive this wave energy. So it's like that. And we can compute these vectors and project onto the map. This is what's going on for the California drought. Okay? And you can trace it back. If you trace it back, then you can start to see where this vector came from. It seems like that the vector comes from here in the western North Pacific. Okay? And so that might be the potential source of the energy. And we're working on the details about that. So putting all this together, what it really means is that the California drought, we know, is linked and very closely linked to meteorological forcing, which in this case is dipole. And the dipole we found is connected to the development phase of the El Nino, or what we call ENSO precursor. Okay? And there is a trace of global warming in this forcing, making it become so extreme because of the model simulations. And in terms of short-term thinking, what it really means is that, well, this relationship means that El Nino is coming. Okay, how do we know that? Well, through historical data. And if El Nino does form this coming winter, empirically we know that you bring wetness to California. So probably will relieve their long-term drought somehow. Okay, so this is the not the latest, but probably like from last month about the IRI CPC El Nino prediction, and then CPC has launched El Nino watch. So it's going to, you know, the direction is about the same. Okay, so what that really means is, if you look back, there are higher precipitation winters, which usually associated with El Nino. Okay. Although the year before it was actually dry. What I mean is, maybe this coming winter, it can get a little bit wetter and bring relief to them. Okay? So looking forward, well, we know that extreme weather dry and conditions may happen, and with the growing population in California, even just 1 year of drought can cause huge impact, just like this past year. But I believe that we could really learn from Australian success, because they had the prolonged drought, much longer drought in the US, and the intensity was greater too. But their agricultural productivity, for example, recovered within 1 year. After just a few years ago, the worst drought ever recorded. Why? Well, this is a summary that is summarized by a science piece of communication, where they built water markets, okay, and irrigation system modernization. But the one that US is lacking right now is clear water entitlements. So farmers, water managers, they can easily trade water rights, and then they can offset all those of the stress that they are experiencing. And that is something is just being exposed by this California drought in the Southwest. And finally, this is the paper we just published. This way is the source of hate mails that come into our email box. With that, thank you.